Okay. Hi, my name is Leandro Lucarella. Maybe some of you know me by Luca from the forums or IRC chats. I work at Sociomantic Labs, one of the sponsors of the conference. These slides was supposed to look much better, but I had to make some last-minute corrections, so I couldn't send them to the design team. But hopefully for the end of the conference, they will be ready and will be uploaded. So I'm talking about Concurrent Garbage Collection in D. This was my thesis. And first I'm going to do a quick introduction to Garbage Collector for people that don't know about it. As far as I saw, a lot of people knows about it and knows the problems in D about the garbage collection. Hopefully, my suggestion is to fix one of these problems. I hope it works. So what's garbage collection? Basically, it's automatic memory management. So you don't have to ask for the memory and then return it yourself. What is it for? One of the main ideas is to simplify interfaces. The problem with manual allocation is also that each time you call a function, if these functions return some memory, you need to specify if that memory is handled by the function or if you have to free it yourself. So that's a quite important point that sometimes is missed about garbage collection. Another point that it's not frequently associated with garbage collector is improved performance. Everybody here might think that garbage collector is the exact opposite, but I think if it's done right, it could improve it. It's like a compiler. At some point, I think nobody thought that a compiler could do better than a human writing assembly. And at this point, I think you can have some doubts. With memory management, it could be the same. And also, of course, avoid memory errors, dangling pointers, memory leaks, and double freeze, common memory problems. So how to do it? There are three main classic approaches. I won't be talking about the details about this. It's just a quick introduction. Reference counting, I think there is something in Phobos to do that. Semi-space copying is something very popular, especially in Java. And mark and sweep, which is the algorithm used by the current collector. Quick introduction about mark and sweep. Basically, this is a representation of the memory. You have a root set, which is basically the stack, the CPU registers, and the static memory. So from that, you need to know what memory cells are still alive and which are not used anymore. So the procedure is to visit one by one the root set. So the R0 is a pointer, which points to the cell H1. So that cell gets painted when you visit it. So that means it's alive. Then you have to go through the pointers in H1. H1 points to H2. So we visit H2. We mark it to know that it's alive. Then you go to H5. At this point, H5 points to H1 again. But to avoid the loop, since you know it's already marked, you just ignore it. So that way, you avoid cycles, which is a very common problem of reference counting. So that loop is complete because H5 doesn't have any other pointers or any other previous cells. So we visit the second root, which points to H6, same procedure as before. H2 is already marked, so we stop there. So this is the result. The cells marked in white are the free cells, the garbage, and the other one are the leave set, the memory that is still alive. So the sweep phase is just traversing all the memory and looking for the white cells. So this is a very quick introduction. There is more than 3,000 papers about garbage collection. The main goals about garbage collection is reduce execution time, the number of collections. The less collections you made, the less time you spend doing this bookkeeping about memory, to reduce each collection, and to reduce the pause time. This is an important problem. When the collection is done, basically you need to stop all the threads in your program because you need to see a consistent view of the memory. Imagine that if you do this while the memory is changing, then you have to do a lot more of bookkeeping. It's possible to do so, but it's really, really hard because you need to keep track of all the changes in the memory state. So the easiest approach is to just stop all the threads and do the collection and then start them again. Of course, these pauses are very intrusive, and there are programs, like probably games, that cannot afford them because you can just pause for 1 second again. There are different techniques for this. You can partition the memory. This is what generational garbage collection does, if anybody knows them. Then you can add concurrency to the garbage collection. This is what this talk is about. And then you can add time information to do a more precise scanning. And also static analysis. It's another way to improve the garbage collection. For example, to change a heap allocation to a static allocation if you can't ensure that this piece of memory won't leave the scope. Here comes the bad news. I have to go back in time. This only D1 and Tango. Remember Tango, D1? Anybody? Yes. Who knows what Tango is? Interesting. Okay, for those who don't know, in D1 there was a huge fight about runtimes and standard libraries. Tango was an alternative library and became kind of de facto standard library for D1. Fortunately, in D2, we don't have that problem anymore. And also the solution I propose is only for Unix, and it's been only tested on Linux, so sorry for the other Windows guys. Okay, now a little bit about the current collector. Something important to say is also that the D2 runtime was based on the Tango runtime. So everything I will talk here, most of the time applies to the D2 runtime because they are almost the same in some aspects. So basically, this is the heap structure. We have the heap is composed by pools. Pools are just big chunks of memory that they are asked to the operating system using mmap, just a big chunk of memory. Each pool have a set of pages, a number of pages, and each page is divided in blocks. And finally, we have some free lists to keep track of free blocks. So a little more about the blocks. They are fixed size. This means each page here have a specific block size, which might be, for example, 512. We have 8 blocks in page 0 there, and so on. The sizes go from 16 bytes to 4K, which is the common page size for 32 and 64-bit. And the increment is in power of 2, so 16, 32, 64, etc. So as I said, one page stores only one block size. But block of the same size could live in different pages. It's like with the pools. In one pool, you can have different block size as long as the page keep the same block size. Then you have big objects. Any object that is more than 4K, it's stored in full pages, full contiguous pages. And then there are some flags for bookkeeping to do this garbage collection cycle. Basically, the flags are stored in a bit set, which is nice because it's cache friendly. And you have several marks, several bits for this bookkeeping. Mark, scan, free, they are used for different stuff. I won't go through the details for this, but it's important to know that they are stored in a different bit set. So the current garbage collector algorithm is a mark and sweep, as I showed before. It's conservative, so it doesn't have appropriate type information. This means that you can have what it's called a false pointer, meaning that each word on your program will be interpreted as a pointer. So if you have some random number that by any chance looks like an address, a valid address in the heap, then this valid address, the object stored there, will be kept alive even when it might be garbage because some number happens to match the address. A pinch of precision, because if you have an object that doesn't have any pointers at all, then you can add one of these bits marks to say, okay, this object have no pointer, so don't scan it at all. So it's kind of black or white. It's trigger allocation. As long as you don't allocate any memory, the garbage collector will never run. It's stop the world, as I mentioned before. When the collection starts, stops all the threads, make the collection, and then restart the threads. The sweep phase can run in parallel, at least in theory. Another important thing is it has a global lock, which means each time any function from the garbage collector is called, and this includes like changing the size of an array or allocating new memory or freeing memory, all will acquire this global lock. So in practice, the pause time could be extended to the sweep phase, because if any thread that didn't trigger the collection is using the garbage collection, the garbage collector, then it will have to wait until the collection is done to acquire the lock. Okay, so far so good. Many questions about? So this is what I propose to change. First, I have to introduce the fork system call. How many people here know what fork is? Pretty good. Okay, so fork basically creates a copy of the process. The child process have the same structure and memory than the parent, but it's a copy of the parent. So we have a snapshot of the parent's memory, but both processes run in different contexts. So when something is changed in the parent, the child process stays the same, and vice versa. This copy is really more like virtual, because at least in Linux, and I think any major Unix system, the copy is actually a copy and write. So as long as you don't actually write the memory, they share the same pages, and I will show this a little more graphically. And the child process starts with only one thread, the one that called the fork system call. And in Linux, it's very, very efficient. So basically, when you start with the parent process, you have something like this, a page table, which points to some pages in the virtual memory. When you fork, you have a new process with a copy of the page table, but each page is the same as in the parent process, until one of the process, in this case the parent process, changes one of the values, here the by value. This is the state before the change. When it's changed, the operating system allocates a new page, copy the content, the modified content to a new page, but the child process is still pointing to the same page. So this is what gets us the snapshot of the memory. The child process is always seeing a snapshot of the parent at the point of the fork. So what's the trick? The trick is to use this to get a snapshot to do the garbage collection concurrently in a child process. So I didn't invented this. I'm just reusing the work of Gustavo Rodriguez Rivera and Vince Russo. This is a very nice paper. If you want to read it, it's free online. So the parent process keep running the program while the child process running the mark phase. The results are communicated using shared memory, and something that I didn't expect but was a really, really nice side effect is the synchronization needed is really minimal. You don't need to synchronize anything at all. Just do the fork call and the wait period call, which is just to wait for the process to end. But each time the shared memory is used by one of the process, the other one is not really using it. So you don't have to synchronize anything in the shared memory. Just the parent process is forked, the child process will run the mark phase, changing all this. The shared memory is this bit set with the flags. So the mark phase will update all the flags, and while it does that, the program will keep running but will not modify these flags. So when the concurrent mark phase ends, just the main process, the program, will wait for it and just read these flags that were updated in another process. So it's a pretty simple concept, but it has some problems. So the thread that triggered the collection is blocked until the end of the collection. And this can potentially also in the other threads. This is because of the global lock, remember? So as I said, since the garbage collection is allocation triggered, what happens is one thread allocates memory. There is no free memory to fulfill this request. So the garbage collection is triggered, but this thread waiting for the memory just can't keep running because it needs the memory to continue. So it has to wait until the whole mark and sweep is done. On top of that, if another thread needs to use the garbage collector, since the lock is taken, it will have to wait too. So at the end, the real post time is almost the same as the collection time, at least for sure for the process, for the thread triggering the collection, but potentially also for the other threads. So all this effort is not really paying off. So some proposed solutions. One of them, I called it eager allocation. And the idea behind this is to create a new pool before starting the concurrent mark phase. So the actual allocation request can be fulfilled immediately. So at this point, what we have is the process asking for memory. We don't have enough, so allocate a new pool, return the new pool to the requesting thread, and launch the collection concurrently. In this case, all the threads will run really concurrently because no one is taking the lock. The mark phase is running in another process already. So this is a little compromise. You have potentially more memory usage because, of course, you are allocating a new pool when probably you have enough garbage in your program so that if the collection was done, you could really fulfill the request. But on the other hand, we have a guaranteed small post time. In this case, the post time. Yes, question.
What if you had the marking thread simply running continuously at a low priority in the background. So when you're doing an allocation and it might want to trigger a collection cycle, it might look and say, oh, I've got a new set of freed ones that the marking thread has already fixed me up for it. Is that a potential improvement to this?
Yes, it is. There is one, it's not a problem, but something you have to figure out is in that case, you need to add some synchronization points because you need to get these snapshots from the main process. So what you will have to do really is having some thread or something with a timer and launching the collection from time to time from there. You can't really keep one process running all the time because you need to make the snapshot, and the way to do the snapshot is using fork. So you have to start the collection from the main process.
Oh, I see. Okay.
Yeah. Okay, so problem, potentially more memory usage. The good thing is the post time is really, really minimized to fork, and the allocation time. Another optimization, early collection. This is something more in the terms of what Walter says. The idea is basically not to wait until you are run out of memory, but to trigger a collection, a preemptive collection, before the memory is exhausted. So in this case, the program can still run the mark phase concurrently until the memory is really exhausted. At that point, any thread needing to allocate more memory will have to wait for the mark phase to stop. So this also might run more collection than necessary because you need to set some threshold to say, okay, if I have only 10% memory free, I will run the collection. But maybe it's not really necessary because your program is, I don't know, about to enter in a stable state or something like that. So the compromise here is potentially more CPU usage, and you will lower the post time, but it's not guaranteed because if you have any memory-hungry thread or something like that, and the collection is not over and the memory is exhausted, then it will block again. The good news is these two techniques are combinable. So you can use eager allocation to avoid blocking, but you can use early collection to minimize the memory usage. So you try to do collections a little earlier than normal, but if at some point any thread runs out of memory and the mark phase is still running, you just can't allocate more memory and fulfill the request and continue. These are other minor improvements I made to the garbage collector in the way, which is basically configurability. I think there is no silver bullet for garbage collection. I think anybody that believes only one garbage collector should work perfectly with any application is plain wrong. So you have to keep this in mind. The same as a compiler have a lot of switches to optimize one or other kind of usages, the garbage collector should be the same. But I found that in the collector there were a couple of things that you could configure, but it was really hard to do so because you have to recompile the garbage collector to change this behavior. So what I did is to make it what I call initialization time configurable, which means it's using environment variables to set up all the structures in the garbage collector at the point the program initializes. I think this is a good compromise because it's much easier than having a completely dynamically configurable garbage collector, because if you have some option change at any point, you have to keep a lot of stuff in mind. If I'm like in the middle of a mark phase or a sweep phase, and then adjust to all these changes. So I think this works pretty well because you know beforehand usually what your program needs. If it's a long-running daemon, it's a small command line tool or whatever. So you can optimize it when you run it. So the all compile time options were memstomp and sentinel. Probably who here knows these two options or ever have heard of them? Yeah, that's what I suppose. This is very useful stuff, and nobody knows it because it's compile time. The runtime is basically part of the compiler, so if you want to use this, basically you have to recompile the compiler. So memstomp, basically what it does is to just when the garbage collector free any memory, it overwrites it with a pattern. So next time it will reuse this memory, it will check if the pattern stays the same. This can catch some memory problems where something was freed but is still used by the program. So if the pattern doesn't match, it means somebody is still holding a reference to that memory. And the sentinel is to avoid problems with overwriting the buffer overflows or stuff like that. What it does is also writing a small pattern at the end of the memory chunk that you allocated. So if you go just have a buffer overflow there, when the garbage collector frees the memory, also checks this pattern at the end of the memory block. So what I did is make these two options now configurable through the environment variables with this format, like DGC opt and some parameters. And I added some new options. The pre-alloc is not really very important. It's just to pre-allocate some memory. It could speed up the initialization of some programs. Min-free is the threshold for the early collection. It's basically the percentage of memory free you need to have to launch this preemptive collection. malloc stat file and collect stat file, it's just logging. One is for allocations, and the other one is for collections. It just writes, you specify which file to use, and it writes to that file each allocation or each collection with some interesting data, especially timing data, like how long it took. Lately, I worked on adding also the information, the stack frame, the stack trace to know also exactly where this allocation or collection was triggered, but this is not yet ready. Fork is basically to activate or deactivate the concurrent marking. So you can use the garbage collector in the old way too. And eager alloc and early collect is these two optimizations that I talked before. Okay, so we will see now some results. Unfortunately, these results are a little bit old, almost 2.5 years. I wanted to do some testing with our programs in Sociomantic, but I need to do a lot of work because to compare to the old garbage collector, I had to modify the old garbage collector, and that code is already gone. So to do that, I will have to update everything. But I think these numbers shouldn't change a lot, especially for the one that was almost freeze. So the idea is to do multiple runs just to minimize any errors in the measurement. The results were expressed in minimum, average, maximum, and standard deviation. It's just using the average or something, or the maximum, or whatever value is not really meaningful. I think this really covers much better how also the tests do in terms of reproducibility. It's not the same if you have 10 seconds, 1 second in another run, that if you always have 5 seconds. So also to minimize the variance of between runs, I use these commands. Basically, they are just to give priority to the process, to the I/O, and to stick the process with one process to one CPU to avoid migration issues. And I did the test in a 4-core computer. This was really hard to find some testbed programs to test this with, because at that point, and I think maybe now with D2 it's a little bit different, but it's really hard, or it was really hard to find real programs in D out there, especially that they were updated, because it was very common that somebody just made a toy project and abandoned, and since the compiler changed it a lot, in 1 or 2 months, that project will stop compiling. So I had 7 trivial programs which are not really useful at all. It just stress some particular aspect just to try pathological cases. Small programs, this is the Olden benchmark. This was translated to D by somebody you probably all know, Berophil. Yeah, some. Berophile, I don't know how to pronounce it. He was really crazy about benchmarking, and it was useful for me. Thank you, Berophile, wherever you are. So these are relatively small programs, but they perform a real task. They are not just stressing something. But on the other hand, they are not very fair to the GC because they do a lot of manipulation of trees and lists and allocates a lot, but really a lot. So it's not completely realistic either. And then the real programs, this is the most important for me. It's like when you have to test something, you have to use real programs because all these are very interesting to see some edge cases, but this is what really matters. I found only one program for that. It's called DIL. It was a D compiler written in D. It was fairly big. It's 32 key lines of code, 86 modules. 2 other good things about it. It wasn't written with the GC in mind. A lot of people now write code knowing that the GC doesn't work that well, so you try to avoid a lot of allocations or stuff like that. In this case, since I talked to the author of DIL, he told me he didn't thought about the GC at all. He just wrote as if GC was magical and just worked perfect. And also it uses a lot of constructions in the language that uses the GC, like dynamic arrays and strings, etc. Okay, what I measure is the maximum stop the world time, maximum real pause time. The difference between these two, the stop the world is what I call is just the time that all the threads are stopped, like really stopped, not because of the lock, the global lock, but because the garbage collector stopped all the thread to start the mark phase. This is even necessary in the concurrent garbage collector because when you do the fork, you need also to stop all the threads to dump all the registers and have a clean state. So there is some stop the world time in the concurrent garbage collector too. And the maximum real pause time, it's like the moment when the program issued the allocation to the moment the allocation returned. So that includes allocation time, fork time, and everything that ran in the garbage collector. Then the peak memory usage and the total execution time. Okay, first, stop the world time. As you can see, except some pathological cases, this is order, maybe it's hard to see, but this is basically, the first one is the basic collector, which is the original garbage collector, then CDGC, then you have these lines, this is the minimum, this is the maximum, and this is the average and the standard deviation. And the first set, this order in the same order I used here. So the first one is here, and deal is in that corner. OK, so as you can see, even in this case, in pathological cases, except on this one, the stop the world time dropped dramatically. For deal, which is the case I care the most, you can't even see the line here. Also, this is all normalized to a percentage. So this is like the mean is 80%, and this is, I don't know, 0.01 or something like that. So massive drop, but still not completely meaningful because of the global lock. Remember that in this case, even when another thread might be running, if it needs to allocate, it will block again. So this is a more interesting value. But again, it's almost the same pattern. The pathological cases are more random, and then we have also here one of the olden benchmarks that increase in, normally the cases that increase a lot are programs using a lot of threads allocating a lot. So in that case, the memory, this is also using the eager allocation and the early collection. So in the cases where you have a lot of threads allocating a lot, the garbage collector will ask a lot of memory to the operating system. So you will have a lot more memory to mark. So that's also probably why it's taking so long in those cases. But again, going to deal, dramatic change is a little bit higher than the stop the world time, but it's still a huge difference. Peak memory usage. This is where the concurrent garbage collector doesn't do that well. Again, those cases that nobody cares about, in this case, the memory usage has increased a little bit, or a fair amount of change. So here there are a couple of explanations possible, but probably is the eager allocation kicking in. Also, at the point when I did this test, there was a little bug that could also increment the memory usage, but it's kind of expected. As I said, the eager allocation can cause this kind of behavior. And this was a completely surprise for me. I expected that the total execution time increased, but it dropped almost a third. My explanation to this is deal was a single-threaded program. And now the garbage collection is running in another process. And in a multi-core computer, what we did is just basically made a single-threaded application converted to a multi-threaded application. So while the garbage collection is running, the program can keep doing its job. OK, summary now with more concrete numbers. For deal, we have the stop the world time drop from 1.6 seconds to 0.1 to 0.01, sorry. So in terms of interactiveness, like a game or a low latency server, the difference between not being able to use the garbage collector to being able to use the garbage collector. The same for the real post time. This is a little bit higher, but maybe you can correct me, but this should be more or less in the span for a frame, or?
Put another 0 on it.
Sorry?
It needs another 0.
Yeah, OK. Well, then we need a little more work to do. But for any other low latency, at least for anything that you don't need the user to detect, I think 0.045 is pretty decent. The big memory usage went from 200 megabytes to 300 megabytes. So it's worse, but considering the memory available nowadays, I think it's not that bad. I will pay the price to have the small pauses if you need it. And the total execution time from 55 seconds to 20 seconds, pretty impressive for me. So this means stop the world 160 times lower, post time 40 times lower, peak memory usage 50% higher, and the execution time it's lower by 3 times. Some problems, limitations, and outstanding issues. The memory usage is clearly one of the main problems, probably because of error allocation. I think part of the problem could be solved already because of this bug fixed. And probably another thing that I didn't do with this test is to hand tweak the parameters like the threshold for the early allocation, early collection, or so this might be tweaked like using different parameters. And the second one is an important one, a really nasty surprise, but there is a possible deadlock when using the glibc. The glibc uses an internal lock. And since the thread stop is done using signals, when you use the only place where I see this happening is with malloc, with like with the libc malloc. So if you use external C programs, and the malloc gets interrupted by a signal when the lock, the internal glibc lock is taken, then when you fork, the fork also tries to get the lock, and since the thread stopped, the malloc will never return, and you will stuck in the fork. Anyway, the details are in a bug report in Tango, but this is not going to be changed in glibc. I think there could be some ways to get around this. But it's important to notice that this doesn't make it completely useless. This is still useful in the real world. We are using this garbage collector for almost 2 years now in Semantic, and it works, having these things in mind, it works well. Some future work, I didn't mess up the sweep phase. Very common optimization is to do a lazy sweep phase. Basically means that you don't sweep until somebody is asking for more memory, so you can split the sweep time more evenly between allocations, so you can reduce the pause time. Concurrency, I found also that the global lock was really disturbing when trying to achieve concurrency. And try to figure out this related to the glibc problem, try to stop the world without using signals. Besides that particular problem with libc, also using signals is very disruptive to programs because it's something that it should be available for programs. And right now, the runtime in this using 2 signals for internal usage. Any questions? Yes, Walter?
I'm not sure why, I thought you eliminated the stop the world, so why are you having a problem with stop the world?
I didn't eliminate stop the world because to do a fork, I need to first get all the threads stopped and dump the register to the stack so I can scan those registers. So it's a really tiny time because it's only for the fork that you need to stop the world, but you still need to do it.
Why doesn't that happen when oh, because it's not doing fork, okay.
Yes, whoever have the microphone.
So actually I have a couple of questions, but I will go with the easy one first, at least I hope. So I understand that this stuff, and I'm mostly a Linux and OS X guy myself, is strictly POSIX only because it depends on fork.
Yes.
Are there any like similar cores that could be used on Windows? Do you know? Or does
if
anybody
anybody
know?
knows, would be interesting to know, but I don't really know.
You might be able to leverage the debugger or something.
Sorry?
You might be able to leverage the debugger to get introspection.
I believe we've actually discussed this question before. With Windows API has a function which allows creating sharing memory between processes. So there is a way to map memory in another process, which is copy on write. So copy on write is really the magical thing that makes this whole thing work as I understood it. So if you just follow the API, it should be possible to create a satellite process for the main Windows process, which performs garbage collection in the background. I think I've also, don't quote me on this, but I've read somewhere that it's also possible to do it within the same process, but only on NTU versions of Windows, which is really everything we care about nowadays, since we don't care about Windows 98 anymore. So I think it's definitely a possibility that we could look into.
Okay. Yeah, I think anyway that when the garbage collector becomes so close to the operating system, you can share a lot of code between different implementations of the garbage collector, but if you really need to do something very performant, you probably want to keep different implementations for different operating systems. Because of this difference, maybe when you can even do this in Windows, seems like the approach is quite different, like just forking. Yes.
Do you ever unmap or unmap the pools, or can the eager allocation just completely exhaust the address space?
That's an interesting question. The pool that you allocate, it's just another pool. It doesn't have any special treatment. And the only way the garbage collector can return some memory to the operating system is by having a full pool free. So, well, I don't know if it's worth doing, but if we go back here. So the only way to free memory is, for example, this will be a more extreme example. You have 64 blocks of 64 bytes, for example, here. So to return this pool, you have to have all these blocks free. If only one block is still used, this will never be returned to the operating system. I think that's another area where the garbage collector could use some work, because it can be pretty hard to eventually return some memory to the operating system.
So
That's also a reason why I think the memory increases so much, because once you have acquired memory from the operating system, it's really hard that you could ever be able to return it.
So what I'm wondering is, how does, with the eager allocation, if you did strictly eager allocation and no early mark and sweep or whatever the other side was, every time you do you actually run a mark and sweep, you just allocated a new pool.
Yeah.
And if you do that long enough, I would expect you'd simply completely exhaust something.
Yeah, well, there is another, even when it's not a special treatment, there is another property of this eager allocation, that the pool that you will allocate will be the size to fulfill only that request, so probably will be quite small. So if you are using most of the memory by that allocation, when you free it, it's more likely that the whole pool could be freed. So even when, it's very disruptive in terms of memory usage, should be more or less regulated by that.
So they actually are freed if they are completely unused?
When they are used, they are freed, yeah.
Okay.
I wanted to ask about that. Of the stop the world time, rather when nothing is running, I think that was 45 milliseconds or so in your slide.
Stop the world.
Do you know how much of that is due to the fork itself, and how much is something that in your code?
Yeah, I think the stop the world is mostly measuring the fork time. It's a fork time plus a little bit of this. You need to dump all the registers to the stack to be able to use that as a root set. But yeah, this is the slide that you wanted to see, I guess.
But I guess if it's fork time, we
yeah.
don't have too much hope of making it 10 times smaller, right?
Sorry?
If it's just the fork time, there is not much hope of making it much smaller.
Yeah. No, but that's also an interesting point, because when the memory increases, the fork time increases too, because you have to copy much bigger page tables. So if you are working with really big amount of data, that could become an issue. Yeah.
So my next question is actually in the same direction, more or less than the previous one, which is what kind of code have you actually used this on at Sociomantic? Is it like long-running server code or?
Yeah, there are long-running servers, but same as Remedy Games, we pay a lot of attention not to allocate and to reuse buffers and everything.
Because I mean, like DIL is a short-running command line tool, so yeah.
Yeah. This test was before, I think, almost before Sociomantic was born. So.
So by long running, what kind of uptimes?
Until it crashes. Until it crashes. As long as possible.
And one last thing I was kind of hoping to like stimulate discussion on is in D2, which is not something you guys are doing as far as I'm aware. We actually have like thread local by default. So we could actually have thread local GC. And I don't know if this would like completely save us from stopping the complete world. We only would ever have to like do it per thread, except for shared memory, which ideally we could mark up as shared, even if that's not quite finished yet. So I don't know, maybe we can like figure out a plan to make something happen in this regard, because there should be some quite nice savings in like interruption time there. If you're only like collecting your pools to scan and everything would be smaller, and you would only have to stop one thread. And I think D should be able to actually have a quite small, like global shared memory set if you can do it per thread.
Yeah, I didn't thought about like the details of how to implement it. I know it should be possible. There is literature about it too. Also, that technique also enters into this, like that's partitioning the heap basically. So it's like a generational or other techniques. So I think it will be good. I think for D2, there is even a lot more room for optimization, also with immutable. If you know some piece of memory will never change, you can cache that information in the GC and maybe not scanning all the time, but just store a couple of, like, pin. If you have some memory that will never die and it's pointing to some other block of memory, you know that memory will always stay alive as long as this one stays alive. So you don't have to scan this all the time. So I think in D2, there are a lot more of like optimization opportunities. Thread local will be another one. Yeah.
So I was wondering about your problem with the real pause time in terms of during the mark phase, you're holding the GC lock. I wonder if you could release the GC lock during the mark phase, because all that's going to come back from the other processes, which bits to free, those aren't going to change even if things are, you're allocating more memory or whatever.
In the concurrent garbage collector, the lock is freed immediately. During the mark phase, it's not taken.
It's okay.
Yeah, no, it's at least when you use eager allocation or early collection. If there is any way to fulfill that request, then the mark phase will run in parallel without taking the lock.
So it's just during the sweep phase that you have to, prevent
exactly.
other threads from.
The way it works, I didn't mention that. Next allocation, the garbage collector will check if the mark phase is done. If it's not done, either will block, or if eager allocation is enabled, it will return more memory. And then when the mark phase is done, the sweep phase runs. That also is blocking the process. So that's why I think the sweep phase could also use some optimization, like lazy sweeping or something like that.
Okay.
Is lock-free sweeping a possibility?
Sorry?
Is lock-free sweeping using CAS or something?
Sorry, repeat the question.
Is there a lock-free algorithm we could use for the market sweep?
Could the data structures that keep track of what's allocated and what's not be made to be updatable without taking locks, like using CAS or something?
I guess they could. There's another problem with lazy sweeping. It's in the sweeping phase, you have to also run the destructors. So if you do that in parallel, you have to also have some, I don't know exactly, maybe Walter have an answer, if there is any definition in the language about if the structures can be run in parallel or something like that. Just.
I think they can be run in parallel at the moment anyway, because the GC log is.
Actually, I think there was a requirement a long time ago. There was a Tango bug where, in a destructor, if you were doing something and that required a mutex in C or something, some other thread could have been holding onto that mutex. So you actually have to release all the threads during the sweep phase. So I think you could potentially do that.
Yeah,
And
that's a problem I'm seeing. I think the language doesn't say anything about like you have to.
I think the only thing you would need to do is to take the lock to set the different bits to tell whether the block was free or not, because that's stored in a separate location.
You should be able to do that with the cast as well.
Sure.
I have a question. Have you measured the time that the copy on write needs in the running process?
No, that's an interesting question too. And that's another problem. If you have a program that mutates the memory a lot, it can become a problem. Also because you will need more memory. Now you have two processes running, and if the main program is modifying a lot of stuff, then that copy and write magic will not work anymore. So yeah, it's something to have in mind, and I didn't do any measures about that.
On the other hand, one thing you can rely on with copy on write is it's a critical operating system function, and the operating system vendor usually expends an enormous amount of effort to make sure that that goes fast.
Yeah.
So that's one thing where you're taking advantage of all the work by the operating system people.
Yeah, that's one of the beauties of this approach. It's really, really very simple. It's like most of the time I spent doing this was researching other stuff or maybe looking for programs for the testbed, but once I had everything in my mind set, implementing it was just extremely easy because most of the work is done by the operating system.
I have another question about that deadlock problem you've been having. Does the concurrent thread ever call anything in glibc?
You mean the one running the mark phase?
Yes.
No.
And it still deadlocks even though it's not calling anything?
Yeah, because it's before it forks. It's if any thread has called the malloc function, and the signal arrives when it's inside malloc, and with the lock taken, the stopping of the threads it's done before the fork. So when you try to fork, the forks try to get the lock, and the other lock is taken. The threads are stopped, so deadlock. That's one of the approaches I want to try. I don't know. I mean, also, if they have a lock, I guess it's for a reason. So,
could you take?
But it's one of the approaches to try.
Could you take the once you get the registers from the threads, couldn't you just exit the signal handler?
Sorry, repeat.
Couldn't you just exit the signal handler once you take the registers from the threads?
No, I don't think so, because you need to stay paused until the fork is complete. So you need more time than that.
You need a fully consistent view.
Yeah, I don't know, maybe trying to minimize or getting another way. Well, that was part of also the future work. I think probably the best way to go will be to find any way to stop the threads without using signals, or to get the information without stopping the threads, or I don't know if maybe this also when you have to see if you want to go to one specific operating system, because probably if you stay with Linux, you will have some kind of system callbacks or something to stop the threads or something like that.
I'm afraid we're out of time, so let's give Leandro a big hand. All right, so minus 1 minute break, and then we're ready for the panel. So let's take a real quick break and